Remember, this is a big problem because you cannot divide by 0. So that's the first thing that we need to be careful about, is making sure that the denominator of our rational expression does not equal 0. So in this first example, the only thing we are concerned about is that the denominator, 3x minus 2, does not equal 0. We can solve this like we would a normal equation by adding 2 to both sides, and then dividing both sides by 3, which means that x cannot equal 2/3. X can be any other value, but x cannot be 2/3. A graph for this would look something like the following, where you can have anything before 2/3 in the negative infinity direction, and you can have anything after 2/3 towards the positive infinity direction. But the problem is, at exactly 2/3, you have a problem. You cannot use 2/3 because it makes the denominator 0. To write this in set builder notation, what we'll do is we'll use our little set builder braces, and we will say that our variable is x, and we want only x's such that is what the line means, is the such that x cannot equal 2/3. The interval notation, on the other hand, is the actual graph we have drawn out above. And we need to read this from left to right. From left to right, notice our graph starts at negative infinity and goes up to 2/3. Notice we can't include 2/3 because this is what makes our denominator equal to 0. So we will use a parentheses here. We also want to include everything after 2/3. So starting with a parentheses, because again, we cannot include 2/3, we can go all the way off to all the positive values towards positive infinity. To put these two together, we need to put a little symbol in between. It's a U. It unites the two sides. It's called a union symbol. For the next example, we have the same problem. The denominator cannot be equal to 0. It's just that the denominator here is much simpler. The denominator is x. So saying that it cannot equal 0 means that the only value we cannot plug into our function is 0 itself. So our graph would look very similar to the last problem, but just with the gaping hole at 0 instead of 2/3. So for the set builder notation, it would look very similar. You'd use your set braces and your x with your such that line. Well, what kind of x's do we want? Well, anything but 0. So we will input x cannot equal 0 into our set builder notation. For the interval notation, we have to be able to read our graph from left to right, starting with the negative infinity side. Remember that negative infinity, no matter what, will always have a parentheses, as will positive infinity. We can go all the way up to 0, but we can't include 0, so we'll use a parentheses because this is what will make our denominator equal to 0. We also want to include the other side of 0, so starting at 0, we want to go off all the way to positive infinity. And again, we'll put our little union or uniting symbol in between. Now, since we're talking about fractions, we also want to talk about the next logical step, which is, what do we do to all fractions? We have to make sure that they are reduced to lowest terms. So, for example, if you had a fraction such as 14/20, the issue would be that it is a fraction, but it isn't reduced. So, without thinking, you would probably say, well, both 14 and 20 are divisible by 2. So you can divide out or cancel out a factor of 2 from the top and the bottom of the fraction to obtain the reduced fraction of 7/10. That would be your finalized answer. We still need to do the same concept with our rational expression. fractions. But in order to cancel out a factor from the top and the bottom, they must be identical. So we can cancel out any factors that are identical, that are on the numerator, that also are on the denominator. For example, if you look at problem A here, it is already factored, so we can look at what can possibly cancel for us. Notice the x minus 4 on the top and the bottom are identical. So we can go ahead and cancel those out because there's one on top and one on the bottom. Also, notice that there is a common factor of x's on the top and the bottom. Notice that there are 3 x's on the top and 2 x's on the bottom. So we can cancel out 2 of the x's from the bottom with 2 out of 3 of the x's that are on the top. Notice that leaves us with 1 remaining x. Notice though where it is. The leftover x is on the top of the fraction, and it will stay there. So our final answer is just x. Notice everything on the bottom has canceled out. So if we were going to write something, we could write that it is over 1, but it's not necessary because anything divided by 1 stays the same. So we will just give our final answer of just x. Moving on to the next problem. Again, notice that they've already factored this. So we can jump to just reducing and canceling what is identical. Well, notice on this next one on B is that they have a common factor of 2x plus 7. So we can go ahead and cancel out that common factor of 2x plus 7 on both the top and the bottom of our fraction. That is the only factor that is both identical on the top and the bottom of our fraction. So that is the only thing that we can cancel out or reduce out of our rational expression. This leaves us with the result of x minus 1 on top and 2x plus 3 on the bottom. Notice we don't need to write the parentheses any longer. The reason why they're not needed is because the expressions x minus 1 and 2x plus 3 are now by themselves. So they don't need so we don't need the parentheses around them once they are alone.